Those last couple oceanic movements that we haven't really talked about yet, which are those coastal currents as well as waves, take place in what's called the littoral zone. This is basically just the area directly along the coast. It includes these thin strips where land and sea meet, and when they meet, they can take a number of different forms based on the processes that are going on in an area. Other geomorphic agents we've touched on briefly before, like wind, those sea and land breezes can impact coastlines, but really when we're talking about littoral zones and what goes on there, it's the distant winds that have the greatest impact that result in waves and ultimately that result in currents along that coast. Those two things, the waves and the currents they cause in the littoral zone, have a tremendous influence on what a coastline will look like and how that coastline changes over time. Coasts are also really important because they're areas that we really value. There's a lot of hazards to humans in coastal areas. There's also a lot of conflicts between human priorities and demands and the natural processes that would be occurring in the absence of humans. So we're going to look a little bit into each of these things in this video. So again, by far the most important agent acting on the littoral zone are waves. So there's some influence from wind, but really that wind from really far away, as we'll see, that kicks up a storm in a distant part of the ocean and results in waves pushing towards the coast, has the biggest influence on the coast. So nearly every wave that occurs is generated by wind. When energy is transferred from the kinetic energy of moving air to the kinetic energy in water, you have a wave. If you have a high velocity wind, really fast moving wind with high kinetic energy, and that's blowing in a persistent direction over long distances, you'll get waves. However, where these waves start, they won't look like this wave. This is like a nice wave near the coast. What you'll actually get is going to be more like this. Waves start in areas of basically storms out to sea. In areas of poor weather, you get tons of wind resulting from those cyclones and that fast wind rushing into the low pressure center of a cyclone usually. In these areas, there's a significant degree of randomness as to where these fast gusts of wind blow over the water and which direction they're going in. What you really end up with are just choppy seas where wind is blowing in every direction, but a lot of energy is being transferred from the atmosphere to the water of the ocean. These are wind waves out to sea. The size of these waves where they're being formed out to sea, again, depends on a few different things. I mentioned them before, but now we're going to put names to them. It depends on the velocity of the wind, how fast that wind is, how much energy it has that's being transferred to the top layer of the ocean. Fetch is the second variable. Fetch is the distance over which that wind is blowing. If you have wind just blowing over like a small lake, it's not going to make giant waves, even if it's like a really strong wind. But if you have strong wind blowing over hundreds of miles, then you're going to get much bigger waves. Finally, duration's important too. If you get one big gust of wind, that's probably not going to create a giant wave in the ocean. But if you get wind blowing substantially for days at a time in the same spot, a lot more energy is going to be transferred to the ocean in that spot, and the waves are going to get bigger over time. So the velocity of the wind during a storm, the distance over which that storm acts, transferring this energy to the water, and the amount of time that both of those things are working together result in the size of waves that you get. But again, right where they're developing, you're going to get these messy, choppy wind waves, not the nice waves you see surfers riding at the coast. But because a wave is just energy, once it's transferred to the water, it can travel as energy away from that area where it was created or transferred to the water. So we get movement of water beyond where the force is initially applied. That's that blue arrow right here. So looking at the figure, we have wind blowing over a significant distance, that's the fetch, for a substantial amount of time, that's the duration. And if that wind's fast enough, with all those other things, it'll kick up big waves. After that energy is transferred to the top layer of the ocean, those waves are going to advance outside of this area where they were created. Once this energy moves out of the area it's created, out of that area where a storm is happening, the energy is called something else. Once they're set in motion in a specific direction and they keep moving in that direction, over time they join together and become fairly organized lines of energy, like you see in the bottom left. Once they're outside of this area of formation, they're called swells instead of waves. The form of energy in which they exist is still called a wave, but when they're traveling through the ocean, they're called swells, moving in these highly organized lines throughout the ocean. So once swells are moving in the open ocean, they have a few properties. They're still a wave, remember when we're talking about how they're traveling. They're these oscillating movements. They're simply energy moving through a medium. And what we usually consider a wave is actually just the crest of a wave. There are actually a few more parts to it that define the wave. Wave height is described as the distance from the trough, which is the bottom of that waveform, to the crest, which is the top. Basically, the lowest point to the highest point is the wave height. Then wavelength is the distance between one crest and the next crest. Then each wave has a period. That's the time it takes for one wavelength to pass a point. So if you're just like sitting in a boat, the waves pass beneath you. The time it takes for you to get from the top of one wave, for that wave to move, you drop into the trough and get lifted up again by the next wave. The time it takes for that to happen is the period of that waveform. All these properties can differ substantially depending on how a wave was formed, and also the distance in time and space between where we are observing this wave and where the wave was formed. So looking at these different characteristics of waves, out in the open ocean, waves can get really large. Again, in this slide right here, we're looking at wind waves that are happening in the middle of a giant storm. During a storm like this, there have been waves over 100 feet measured. But as we saw, once storm waves become a swell and leave that area where they're being created, they usually become more organized, and they're not in that area of maximum energy transfer. They spread out a little bit and generally get smaller in size. So a swell looks a little more like this. Out in the open ocean, you probably wouldn't even see it at all. This is a swell that's probably pretty near the coast. Generally, again, outside these stormy areas, they're just harder to see. But still, they might range up to about 5 meters in height, maybe about 16.5 feet, and they can have much longer wavelengths, even up to 30 meters or 100 feet. Open ocean swells that are removed from this area where they're created generally have a smaller height, but a longer wavelength and a longer period than those wind waves that are being kind of created by wind in an area, which might be really big, but they're going to have a pretty short period, and they're going to have a short wavelength as well. All right, and what's really important to get about these waves, just to drive this point home, water isn't moving when a wave passes. At least not moving significantly. It moves a tiny bit, but it's not actually moving all the way with the wave. What we have is called orbital motion for the water molecules. A water particle or a small area of water takes a circular, vertical path rather than a horizontal path as that energy is transferring through that water. When the wave approaches, that water molecule or parcel rises up to the crest due to the energy of the wave. Then once that wave passes, it drops down to the level of the trough, finally returning to the level it started. So an individual water molecule will follow that circular path seen to the right of the figure on the slide. It'll get lifted up, and then it'll fall back down. It's only going to move a tiny direction in the overall direction that that wave is moving. And then it's also important to point out that the energy of a wave only reaches so far down into the water as well. It actually gets weaker because remember that energy is being transferred from the wind. The wind isn't really transferring any energy into like the deep ocean. It's most present right at the top of a body of water, and it still has some presence a little ways into the water, but it dissipates as you get further from the surface and eventually goes away, and there's not actually any movement of the wave at all. The depth, which is really important for discussing breaking waves, is half of its wavelength. So if you have a wave with a 50-meter wavelength, that means it reaches 25 meters of depth into that body of water. So that's visualized a little better at the left side of this figure here. We have that circular movement of individual water molecules shown with each one of these crests of the wave. If you look way over to the left, you can see that the influence in the movement, that orbital movement related to the wave coming through, actually decreases as you get further down into the ocean in a deep ocean area. When one of these waves is out to sea, it can travel for long distances without losing any strength. The wavelength, height, and period, none of these really change or diminish over thousands of miles. Once they enter a shallower water area, however, the lower extent of the wave starts to feel the bottom. Now those individual water particles are actually transported forward. Now you get a little more horizontal movement. We go from having this orbital movement within the waves to waves of translation, where these water molecules are actually being pushed forward and surging forward onto the beach. So again, the depth of a wave is half its wavelength. So at that depth, the wave changes form. And we can see that in the middle of this slide right here. Those first two columns on the left are those stacked orbital movements corresponding to the crests of waves. The water within those areas is moving up and down. When that wave gets closer to the coast and the depth of the ocean gets less, the bottom of that wave begins to feel the bottom of the ocean there, and you get a couple different changes to the wave form. So first you get that orbit of water within the wave is made more oval. It projects particles a little bit forward instead of just straight up and down. And we also get those parts of the wave that are touching the bottom of the ocean actually slowing down because there's the force of friction from the bottom right there. The rotational energy higher up continues forward faster than the bottom now because the bottom of that wave is slowing down. Finally, the ground, as it gets shallower and shallower, is actually pushing the rest of that wave upward. All these changes happening at once result in changing from that rotational energy into forward pushing energy. This is where we start getting waves like what we might see at the beach. And eventually these processes push the wave up so high, the gravity has to push it back down, causing it to break. That's where we get a breaking wave. That's towards the right of this figure over here, when we have that water getting shallower and shallower until the top of the wave kind of gets pushed forward in front of the bottom of the wave, and that top of the wave descends back down due to gravity. So this is a breaking wave that's made it from a storm a long ways away. This is actually a pretty big wave. This is something like a 10 or 12 foot wave that I saw on one of my trips back home to Santa Cruz. And the fact that it's pretty distant from that broken wave in front of it, that line of white water that you can see, that means it's a long period wave. That means the two crests, where that white water is and where that wave is actively breaking, are pretty far apart. That means the period's going to be pretty long. But finally, that wave hit the bottom. That caused the growth of the wave, that top part of the wave, to move faster than the bottom part of the wave and eventually topple over forward in front of the bottom of the wave. You get a nice big barreling wave like this. So a couple more features of a breaking wave. After it breaks, it runs up on the shore. We have this water that pushes forward up the shore that's called swash. That's pretty important for moving particles around on the beach. And then a certain amount of that backwash pulls back out off the shore due to gravity. According to what we've learned thus far, we wouldn't get nice waves that have peaks like we saw in the background of the slide. We'd get these like straight walls of water all breaking at once, like in the right on the slide right here. What we actually see in the real world are waves breaking in all sorts of different ways, depending on a few other important variables. Only in some places do they all break at once, like in the slide. And just as a note, that's actually me in that slide. I paddled out at the wrong place at the wrong time and got absolutely destroyed by this wave. What we really get are differences in the ways that waves break in different places due to two processes called shoaling and refraction, and how these two processes work together dictate how a wave breaks in a spot. Shoaling refers to the interference of the sea floor on the wave. So right when that wave starts to hit the ground, slow down a little bit, and the movement of those waves becomes more translational and pushes forward more, that's shoaling. And then differences in shoaling are caused by refraction. So the speed with which shoaling occurs in slightly different places, making waves appear differently, that's caused by refraction. When one of these waves approaches the coast, based on the depth of the features along the coast, we actually get different parts slowing down at different speeds. If you have a curved coastline, a sandbar, or a headland, like you see in the bottom left of the slide, or a reef, any of these things might cause a wave to slow down in that location first. The wave slows down first where it gets shallower because we get shoaling in that location first. If you get shoaling in one location, the rest of the wave actually keeps moving more rapidly as it was moving before. So now there's multiple parts to the wave. There's a slow-moving shoaling part and a fast-moving part that's bending towards that shoaling part. And this can actually cause the buildup of a wave into an even bigger wave. So in the top right, this is Jaws. It's a famous big wave surf spot in Maui. There's a big reef there under the shore. Once these open ocean waves start to shoal and hit that reef and actually feel the bottom at that reef, the wave slows down a lot in the middle for that part that corresponds to like that location directly over the reef, and both sides keep moving forward more rapidly. So only that middle part that starts shoaling first, that's over the reef, actually breaks first. We see the same thing on the headlands in the bottom left. Initially, all these swells start moving in towards the coast in the same direction, but the headland sticks out more. That means you have shallower water close to that headland. The waves move more slowly towards that headland and end up curving towards that headland because the parts of the wave that are further from the headland are actually moving faster. So you get curving in towards the headland, then you actually get divergent wave energy away from that headland as like that wave energy is actually dispersed over larger areas. So what's actually happening with this wave is we likely have a sandbar out to sea. So a sandbar is an area where sand has built up and it's shallower than in other areas nearby. You would have gotten a straight swell line coming in towards this beach. Wherever that swell line hits the sandbar first, it's going to start moving more slowly than other areas, and it's going to break first as shoaling occurs. Either side of that wave that's not shoaling is going to be moving faster than the part that is already breaking.